SwayamPrabha. Digital India. Educated India.
So, welcome back to one more lecture on introduction to soft matter. As we were discussing last time, we were discussing objectivity and its impact on the Cauchy stress tensor. And we had seen that given a general, any general frame invariant tensor, let us say T, the time derivative of T is not going to be objective. So, here basically the reason we were doing this is because we had already said, so we know that the Cauchy stress tensor is objective. But what we proved earlier, it implies that the time derivative of this is not objective, Similarly, so we also saw that the original governing equation had an epsilon dot term, right. And what happens is that the gradient of the velocity field is also not objective. Okay. We are going to skip some of those calculations. So, I will just mention that, and we are going to today just look at the consequence of all this. So, it can be shown that the gradient of velocity is not an objective tensor. Okay. But V plus, so the gradient of V plus the gradient of V transpose is objective. So, in the actually the Navier-Stokes equation, the gradient of V, this quantity usually almost all books would call this capital D. The Navier-Stokes equation is given in form of this capital D, and now you can probably appreciate why, because the gradient, you cannot just take the gradient of velocity because that is not an objective field. There are other, it also comes because of other reasons which converge to the same idea, but this quantity is objective, and to create a good working constitutive relationship, let us say for Eulerian fluids or for an Eulerian system, you would want to use D. So, what happens is that the Maxwell model can be generalized to other forms, okay, to what are called nonlinear Maxwell models. So, nonlinear Maxwell models, and you can generalize them just by using the expression that we had used before. Okay. So, we had some lambda, which is a relaxation time scale or a characteristic time associated with this, and then we had a derivative. Okay. So, some d dt here. So, I am just going to write d dt right now of the stress tensor. So, now we are generalizing it, see. So, it is no longer one dimensional. So, that is why we have to use the tensorial form plus the stress tensor itself into, now sorry, this is 2 delta, right. So, this is 2 eta times d. Okay. So, instead of epsilon dot, we have to use this particular term. So, this now has to be some invariant vector. I am sorry, invariant derivative. Okay. And this is where the ideas of different types of invariant derivatives come in, and actually there are many different types of invariant derivatives. The purpose of this class is not to go into details and depths of the invariant derivatives. Remember that this is just an introductory class. So, we are sort of going to leave you at a point such that this is where from where a more advanced course can begin, right. So, the invariant derivative, there are many different forms, and one of them, for example, is as an upper convected derivative, also called the Oldroyd derivative. Okay. So, this equation is often written as lambda, and then there is a triangle over it which indicates an upper convected derivative. And this indicates an upper convected derivative, thus giving us what is called so this equation here is also known as the upper convected Maxwell model. Okay. Maybe I will just write it separately. Okay. So, this is the upper convected derivative, also called the Oldroyd derivative. So, this triangle here, this marks the upper convected derivative, also called Oldroyd derivative, and this model is now my upper convected Maxwell model. Also often called UCM. Now, there are many different types of invariant derivatives, and different forms will lead you to lower convected Maxwell models are also there, then there are other forms as well. And if you try to do this for the Jeffreys fluid, then you end up with a form which becomes what is also called famously the Oldroyd B fluid model. Okay. But the primary idea remains that you need objective tensors in order to be able to generalize. Okay. So, now you can probably appreciate why we discuss this advanced idea of objectivity in this course, and that is because in order to go from the simple one dimensional models into generalizations, you need derivatives which are appropriate, the objective derivatives. Okay. So, with this what we will do is we will end our discussion on the various Maxwell models and the constitutive equations, because from here we start on to something, basically this is where we end for this particular part, because from here on if you have to go on, that you need to a more advanced course. Okay. And I have not assumed that you have a very clear understanding of tensorial mathematics in order to go there. So, we are not proving some of this. So, a lot of these things we touched very lightly, and just so that you have a complete understanding of where this goes and what are some of the when you read manuscripts etc., you will probably come across the upper convected models, Oldroyd B, these terms you will probably come across in a quite often. So, that is why we sort of end this particular section here, so that you have an understanding of that. Okay. So, that now with that brings us to the last part of our course, which is going to be the response to sinusoidal oscillations. So, if you remember, we had discussed that viscoelasticity, there were 6 different tests, right. two of the last points, or the fifth and the sixth point, concern the work done by the material when it undergoes deformation, and then the response to sinusoidal stress history or strain history, right. So, we will look at some of the some important results in that context. Okay. So, the last point or the last important chapter of our course is going to be response to sinusoidal oscillations. Okay. And we will see the mathematics here now becomes very simple. There is we are not going to have any tensors, etc. We are just going to deal with integrals and again start to behave as if the quantities involved are simple scalars. Okay. So, you might recall that the mechanical properties in the beginning of this class we represented through two important functions, the stress relaxation function and the creep compliance, right. So, mechanical properties were till now have been captured through two very important functions, GT and JT, and these were material properties. Right. Obviously, all these were discussed for linear viscoelastics, right. Now, what happens when materials are subjected to sinusoidal stress histories or strain histories? So, when materials are subjected to sinusoidal strain or stress histories, other material response functions become important. Material response functions arise. And these functions are related to JT and GT, but their forms become very different from the initial looks. Okay. So, what we are going to consider is as an input of a sinusoidal strain. Okay. So, consider a sinusoidal strain in time, which is given by this very simple function epsilon naught sine of omega s, and s is time. Okay. So, basically it starts from 0 and goes until infinity. Okay. We are going to further assume that the oscillations are, so we are going to assume, so the assumption here that is going to be required for any further calculation is that the oscillation amplitude is small enough. So, basically this epsilon naught term, this is small enough, and when we say small enough, we mean that such that the material response is still in the linear category. Okay. So, oscillation amplitude is small such that material response is in the linear regime. Okay. So, now we have to calculate, now that we have a sinusoidal strain, what is that we are looking for? We are obviously looking for the output stress, right. So, we had already first mentioned the stress as we had seen the different forms of stress, the generalized forms, and that for example, we had seen that this it can be written as epsilon not 0 epsilon at 0 into GT plus an integral, right. This was the convolution integral. So, it will actually go from 0 to t, and then you can have this g in the convolution form, right. So, and because this was a convolution, we could also switch these, right. So, it turns out that this is not, this form becomes a little bit more difficult to work with. It is easier if you work with this particular. So, we are going to work with this form, where we are just going to switch these two, and we are going to say this is g of s. So, now we know, since we have the form of the input strain, we also have the form of the derivative, right. So, we know that we do not have to write that, we will just write down that epsilon dot s is epsilon naught into omega into cosine of. And before we proceed further, we are going to make one more assumption. Okay. So, before we proceed, we will assume that this g has a particular form. Okay. So, we are going to assume that GT can be written as this g t can be broken up as g of some g of infinity plus delta g at some time. This is some constant, and this is another part which is varying with time. Okay. And we are going to further assume that t tends to infinity. Why this assumption is required will become clear in a minute. Okay. So, you can see that this particular form, if you put g infinity equal to 0, then basically you are modeling a viscoelastic fluid, and if g infinity is non-zero, then you are essentially modeling a viscoelastic solid. So, you can tweak what g infinity is. So, you can keep it as 0 or you can keep it as non-zero, and that is not a problem. Okay. But we will, for the time being, we are going to assume that this is a non-zero quantity. Okay. So, now we have to rewrite this particular equation, right. So, we have to insert this form of the g here. We also have to insert the derivative of epsilon dot here. So, what does this equation become? So, our original equation now becomes, this is now going to become very cumbersome. So, we have to keep track of all the different quantities we are going to write very carefully. Okay. So, we have the first term, which is the term outside of the integral. Let us write that. So, this we had said this is g infinity plus delta g and then you have the integral term, so 0 to t, and here you have to write this is g infinity plus the delta g. Now, inside the expression we are using s as the dummy variable for time integration over time. Okay. So, we are just now going to make it this, and then we also have this epsilon dot t minus s ds. Okay. So, we have two terms here. You have epsilon naught into g infinity, then you have epsilon naught into delta gt plus the term under this integration. So, we can break this up into two different integrals, 0 to t just a second. Now, let us quickly consider this particular term. Okay. We have already provided a particular form of the sinusoidal strain, right. So, this is epsilon naught. So, this particular term is going to be 0. We have a sine function, right. So, this will just go away. And then we have to simplify some of the other terms. Okay. So, since this equation is becoming a bit cumbersome, let us try to simplify each term by itself. Now, here we have this term is going to be a cosine term, right. So, this is actually going to be equal to, if I use my previous expression, this is now going to be epsilon naught omega cosine of omega t minus s, right. So, I will have to expand this particular term over here. So, we have to recall from trigonometry that if you had cos of a plus b, that was equal to cosine a times cosine b minus sine a into sine b. What is it going to lead me to? So, we can quickly see what this is going to do for us, and that is, for in our case we are going to have to deal with a cos of omega cosine of omega t minus s, right. So, what we are going to end up having is cosine, this is equivalent to cosine omega t into cosine of omega s plus sine of omega t into sine of omega s. So, what I would like you to do now is take the expression that we have found and try to insert this over here, right. And one of the things you can easily see that what you are going to have here is this g infinity term. So, you have one integral where you have to expand, the other integral, this particular quantity, this g infinity is common. So, you can add epsilon 0 plus this integral together, right. So, I am just quickly going to write the other this expression, and then I would like you to try and simplify this for the next class. Okay. So, you have sigma t is equal to g infinity plus, okay, sorry, this is, you have epsilon 0 plus integral of 0 to t epsilon dot t minus s ds plus you have integral of delta gs multiplied by this cosine of omega t minus s ds 0 to t. Now, there is a couple of things missing which are going to be, there is going to be an epsilon naught. Okay, just a second, I am just going to erase this because I should have included that term earlier. Epsilon naught omega delta g S cosine of, sorry, there are so many terms. Okay. So, further we have to keep on doing our algebra, we have to keep on inserting the terms, and we are going to obviously use this particular form of cos omega t minus s and put it here. So, we will do that in the next class. Okay. So, I will stop here for the class today, and then we can restart from where we left off in the next class. Okay. So, we will stop here. Thank you.